Welcome to the deep dive. Today, we're digging into a really interesting resource, pen and paper. Exercises in machine learning.
Yeah, it's not your typical textbook, is it?
Not at all. It's more like a collection of mental workouts. You know, exercises with really detailed solutions.
Right, and they're designed to help you really get the theory behind machine learning, assuming you've seen the concepts before.
Exactly. If you've got some background and want to build that deeper, almost gut-level understanding of how things work mathematically.
Mm-hmm. And I think it makes a great point.
Mm-hmm.
We often jump straight to code, right?
We do.
But this book says, hold on, there's real value in actually working through the math yourself, pen and paper.
It forces you to grapple with the fundamentals.
It does. And the authors, they pull this from courses at Helsinki and Edinburgh, focusing a lot on things like unsupervised methods, inference learning.
So our mission for this deep dive.
Well, I think we should pull out some of the core ideas, the key techniques from the book.
Yeah, and explore them in a way that gives you solid insights, especially if you're at that intermediate AI or machine learning level.
Sounds like a plan. Where should we start?
Linear algebra feels like the right place. Exercise 1.1, Graham-Schmidt orthogonalization, that seems pretty fundamental.
Oh, definitely.
When you first learn about vectors, making them orthogonal, it can seem a bit abstract. What's the core idea?
The main idea is you take a bunch of vectors, maybe they're pointing in kind of similar directions.
Okay.
And you want to transform them into a new set of vectors that are all perpendicular, orthogonal.
But they still capture the same, space, the same span.
Exactly. They span the same space. So for two vectors, say A1 and A2, Graham-Schmidt gives you U1, which is just A1.
That's simple enough.
And then U2 is basically what's left of A2 after you subtract the bit that's aligned with U1.
Ah, the projection.
Right. The formula shows it. U2 minus that projection term, U1 transpose A2, U1 transpose U1 times U1.
So we're peeling off the overlap with U1 to find a new direction U2 perfectly at a right angle to U1.
That's the essence of it. And the book shows the proof, that the inner product U1 transpose U2 is 0. They are orthogonal.
Okay. But what if, say, A2 is just a multiple of A1, like they're already pointing in the same direction?
Good question.
Yeah.
That's a special case. If A2 is just 2 times A1, they lie on the same line.
So
when you subtract the projection, you actually subtract all of A2's contribution relative to A1.
Meaning U2 becomes
0, the 0 vector, which makes sense, right? You can't find a new independent direction if the second vector was already dependent on the first.
Right. And this extends beyond just 2 vectors.
Oh, yeah. You can keep going, building up an entire orthogonal basis for the space your original vector spanned.
And if you get a 0 vector later on, like UK plus 1 is 0, what does that signify?
That tells you that the original vector, AK plus 1, was already in the span of the previous vectors, A1 through AK.
So it was redundant, didn't add a new dimension.
Exactly. It was a linear combination of the earlier ones.
Yeah.
So Graham-Schmidt doesn't just give you orthogonality, it also reveals linear dependencies.
Yeah.
Pretty neat.
Okay, cool. Next up in linear algebra, determinants. Exercise 1.2 gives a geometric view.
Yes. Determinants often feel like just, calculating a number.
Right. You follow the rules, get a value. But what does it mean?
Well, this exercise connects it directly to area. For a 2x2 matrix, the absolute value of its determinant is exactly the area of the parallelogram formed by its column vectors.
Oh, wow. Okay.
Yeah, the book walks through the calculation, showing how the squared area relates to the square of the determinant.
And this isn't just for 2D parallelograms.
Nope. It generalizes. A linear transformation, matrix A, applied to any region, the new area, or volume in higher dimensions, is the original area times the absolute value of the determinant of A.
So the determinant is literally telling us the scaling factor, how much the transformation stretches or squishes space.
Precisely. It gives you a real intuitive handle on what the transformation is doing geometrically. The book uses a nice analogy with tiny squares to visualize it.
That's much clearer. Okay, let's move to eigenvalue composition. Exercise 1.3. Eigenstuff is everywhere in ML.
Absolutely crucial. They reveal the fundamental directions or modes of a linear transformation.
So an eigenvector of matrix A, when you multiply A by U.
Its direction doesn't change, it just gets scaled. By the eigenvalue lambda, AOI. That's the key equation.
And the book notes that if you have multiple eigenvectors with the same eigenvalue,
any combination of them is also an eigenvector with that same eigenvalue, which means you can have whole eigenspaces.
Right, spaces, not just single lines. Then the exercise puts it in matrix form, AU, X, or PU.
Yeah, collecting eigenvectors as columns in U and eigenvalues in the diagonal of A. It's a compact way to write it.
And if U is invertible.
Which it often is, if the eigenvectors are linearly independent, then you get the decomposition. A U inverse.
The book uses A, U, E transpose.
Right, where a V transpose is U inverse. If the eigenvectors are orthonormal, which is common for things like covariance matrices, then V is just U.
Making it A, UU transpose.
Exactly. And it also shows the summation form. A is the sum of E times the outer product, the V transpose. It breaks the matrix down into these core components.
Axes of transformation and scaling factor.
You got it. And that connection to covariance matrices in exercise 1.5.
Yeah.
That's the foundation for PCA, principal component analysis. The eigenvectors are the principal components, the directions of max variance.
And the eigenvalues are how much variance is along each direction. Makes sense. Okay, last one for linear algebra, the power method. Exercise 1.6. Sounds practical.
It is. It's an iterative way to find the dominant eigenvector.
The one linked to the biggest eigenvalue.
Biggest in absolute value, yeah. The formula is VK plus 1 equals VK divided by its norm squared. Often E is a covariance matrix.
So you just keep multiplying by the matrix and normalizing?
Right. Pretty much. The idea is that the component along the dominant eigenvector grows fastest. Repeat enough times, and you converge to it. The book connects it back to the decomposition, showing how other components fade away.
Okay, that's a good tour of the linear algebra foundations.
Yeah.
Shall we move to optimization?
Let's do it. Chapter 2.
So exercise 2.1, gradient of scalar functions. We hear gradient all the time, especially with neural nets. What is it fundamentally?
The gradient tells you two main things at any point. The direction the function increases fastest.
The steepest descent.
Right. And the magnitude of that increase, how steep it actually is.
And the book gives two ways to find it.
Yep. Direct differentiation using your calculus rules, or the perturbation method.
Perturbation.
Yeah, you see how the function j changes when you wiggle the input w by a tiny amount? jw plus delta, jw.
Okay. The exercise tries this on jw as a transpose w.
And for that simple linear function, both methods show the gradient with respect to w is just a.
Which makes sense. The rate of change is constant, determined by a.
Exactly. Then it tackles, like JW transpose AW, a quadratic form, and JW2 error 2, the squared norm. Working through those really cements how to get the gradient.
Then exercise 2.3 takes it up a notch. Gradients with respect to matrices. Why is that important?
Super important when your parameters are matrices.
Yeah.
Like weight matrix in neural networks, right?
Makes sense. How does it work?
The core idea is the same, but direction is now in matrix space. So the perturbation method uses a perturbation matrix, H.
Okay.
And it shows the change, JW plus epsilon H, JW, relates to the trace of the gradient matrix times H, trace.
The trace just sums the diagonal, right? Gets us back to a scalar.
Right. And the clever trick is choosing H. If you make H matrix with just one position, I, J.
Then you can isolate the IJ element of the gradient matrix.
Precisely. The exercise does this for JW, trace W, where the gradient is just the identity matrix I. And for more complex ones like JW, WV2, it's good practice.
Definitely seems like it. Which leads naturally to exercise 2.4, gradient descent, the workhorse algorithm.
Absolutely. The core idea is simple. We want to minimize some loss function, JW.
So we need to go downhill.
And the gradient points uphill, steepest descent. So we take a step in the opposite direction.
The update rule. W gets W minus epsilon times the gradient.
WJW. Yep. Epsilon is the step size, or learning rate. Controls how big a step we take.
And how do we know this actually, helps? That it decreases J?
The book shows it using a Taylor expansion. If you approximate J at the new point, W epsilon gradient, you find the change in J is roughly minus epsilon times the squared norm of the gradient.
Which is always negative or zero, since epsilon and the squared norm are positive.
Exactly. So for a small enough epsilon, you're guaranteed to go downhill, or at least stay level. It's the bedrock of so much ML optimization.
Fantastic. Okay, let's shift gears. Graphical models are next.
Right. Chapter 4 starts with directed graphical models. Bayesian networks. Exercise 4.1.
These use graphs to show dependencies, right? What's the big win?
Efficiency, mainly. The graph structure explicitly tells you which variables are conditionally independent of others.
Which means you don't need to specify every possible interaction.
Exactly. You need fewer parameters. Exercise 4.1 has you calculate the parameters needed for a specific Bayes net, using its conditional probability tables based on parent nodes.
And compare that to a full joint distribution without assuming any independence.
Yeah. And you see it's like way fewer parameters. It shows how the graph structure captures assumptions and saves complexity.
Then exercise 4.3 introduces D-separation. Sounds technical.
It is a bit, but it's the tool for reading those conditional independencies directly off the graph.
How does it work?
It gives rules to see if paths between nodes are blocked by the variables you're conditioning on. There are 3 basic connection types.
Serial, diverging, converging.
Right, and conditioning on nodes in those paths can block or unblock the dependency flow. Serial and diverging paths are blocked if you condition on the middle node.
But converging paths, the V structures, are different.
Yes, they are blocked by default, unless you condition on the collider node, the one the arrows point into, or one of its descendants. That unblocks the path. It's a key concept.
So you trace the paths and apply these rules to check independence statements.
That's exactly what the exercise has you do for a given graph and several statements, like is by 2 independent of I9 given by 6 and by 8. You check all paths using the D-separation rules.
Okay, let's move to undirected models. Exercise 4.7, restricted Boltzmann machines, RBMs.
RBMs. Cool models, 2 layers, visible and hidden units. Undirected connections between layers, but not within.
Often used for feature learning.
Yeah. The exercise starts by deriving the conditional probabilities, like PI1V. Probability a hidden unit is on given the visible units.
And PVI1H the other way around.
Right. And using the RBM energy function, you find these conditionals have a nice sigmoid form.
The standard activation function, so it depends on a weighted sum from the other layer.
Exactly. But the joint probability, PVH, and especially the marginal PV,
Right.
Those are tricky.
Why is that?
Because of the normalization constant, Z. The partition function. It involves summing over all possible states of V and H.
Computationally infeasible for most RDMs.
Right. So calculating PV by summing out H is also hard.
The book then brings in the soft plus function, log 1 plus xbut.
Yeah, it's related to the sigmoid. Rewriting log PV using soft plus gives a nice interpretation.
How so?
The terms in log PV start to look like they're measuring how well the input V activates the features represented by the hidden units, with soft plus acting like a smooth feature detector.
Interesting perspective. Okay. Exercise 4.8 moves to hidden Markov models, HMMs, for sequences, right?
Yep, sequential data like speech, time series. You have hidden states evolving over time, generating observations.
The exercise looks at the joint distribution of hidden and observed states.
And how to get the marginal over just the hidden states by summing out the observations. Standard stuff.
What about the normalization constant for PEB, the probability of hidden states given observations?
It shows how that constant relates to an expectation, connecting it to ideas like change of measure. Basically, the observations Y update our beliefs about X. It also mentions the forward view, which is key for inference.
Chapter 5 then talks about the expressive power of these models. Exercise 5.6a asks about converting undirected to directed graphs.
Yeah, finding a directed acyclic graph, DAG, that represents the same independencies as an undirected one given a variable ordering. You want a minimal IMAP.
Minimal IMAP.
It captures all the independencies of the original graph without adding extra spurious ones. You typically add edges based on the ordering, unless D-separation already accounts for the dependency.
And exercise 5.9 highlights limitations. Neither directed nor undirected models are perfect.
Exactly. Some probability distributions just can't be perfectly represented by either type of minimal IMAP. The best IMAP might miss some independencies or imply ones that aren't there. Shows there are trade-offs.
Good to know. Chapter 6, factor graphs and message passing. These look like ways to actually do inference.
They are. Factor graphs explicitly show variables, and the factors functions linking them. Message passing is how you compute things like marginals efficiently.
Exercise 6.2 shows calculating marginals, PA1.
Yeah, messages get passed between factor nodes and variable nodes. A variable's marginal is the product of all incoming messages. The exercise walks through an example.
And it mentions reusing messages.
Big advantage. Once you compute a message, you can store it. Makes calculating related things like conditional probabilities PH1 1 by 2 1 much faster. You don't restart from scratch.
Exercise 6.3 gives more message calculation practice. Then 6.4 introduces the max product algorithm. Different goal.
Yep. Sum product gives marginals. Max product finds the most probable assignment of values to all variables. The single best configuration.
So instead of summing messages,
you take the maximal, then you backtrack to find the variable settings that achieve that maximum probability.
And 6.5 touches on variable elimination order affecting speed.
Crucial practical point. The order you eliminate variables can drastically change how much computation you need. Okay, Chapter 7 comes back to HMM, specifically inference. Exercise 7.2, the Viterbi algorithm.
Right. We saw forward-backward gives marginal probabilities for each state at each time. Viterbi gives the single most likely sequence of hidden states.
The optimal path.
Exactly. It uses dynamic programming, keeping track of the best path to each state at each time, then backtracks at the end.
Exercise 7.3, forward filtering, backward sampling, FFBS. That sounds different.
It is! Viterbi gives one best sequence. FFBS lets you sample multiple likely sequences from the posterior distribution, hidden states observations.
Oh.
It combines the forward pass filtering with a backward sampling pass. You sample the last state, then the second to last condition on the last, and so on. Gives you a sense of the uncertainty.
Exercise 7.4 is about prediction in HMMs, using the model to look ahead.
Yep. Predicting the distribution over the hidden state at a future time, given observations up to now. You use the transition probabilities to step forward. Then you can update with new observations as they arrive.
And 7.5 tackles HMMs with Gaussian distributions. Continuous states. Right. Things become probability densities. It first shows a useful fact. Product of Gaussians is Gaussian, maybe unnormalized.
Okay.
Then it adapts the forward recursion, alpha pass, for continuous Gaussians. And crucially, it derives the Kalman filter equations.
Ah, the Kalman filter.
Yes. For linear Gaussian HMMs, it gives the exact update for the mean and variance of the hidden state distribution given an observation. The Kalman gain term balances prediction and observation.
Wow. Okay. Moving to Chapter 8, Model-Based Learning. Estimating parameters. Exercise 8.1 starts with MLE for a Gaussian.
Maximum likelihood estimation. Fundamental idea. Pick parameters that make the data you saw most probable.
So for Gaussian data?
You write the likelihood, then the log likelihood.
Yeah.
Usually easier. Take derivatives with respect to mean and variance, set to 0, solve. That gives the MLEs. The exercise also mentions checking the Hessian to ensure it's a maximum.
Then 8.2 goes Bayesian, posterior of the Gaussian mean, known variance. How does the prior change things?
Bayesian adds a prior belief. You combine the prior with the likelihood from the data to get the posterior belief. The exercise uses the fact that Gaussian prior times Gaussian likelihood gives a Gaussian posterior. Very convenient.
That's conjugacy, right? Exercise 8.5 talks about that for the Bernoulli model with a beta prior.
Exactly. Beta is conjugate to Bernoulli binomial. If your prior is beta, your posterior is also beta, just with updated parameters based on the data. Counts of successes, failures. Makes Bayesian updates easy.
And 8.3 looked at MLE for Bayesian networks with discrete variables. How does the network structure help?
Immensely. The log likelihood decomposes, becomes a sum of terms, one for each conditional probability table, CPT, in the network.
So you can estimate each CPT's parameters independently, just using the relevant data counts.
Precisely. Huge simplification compared to estimating a full joint distribution. Exercise 8.3 recalls the simple Bernoulli MLE, and 8.3 entails it to the CPTs in the network.
Okay. Exercise 8.9, factor analysis. Dimensionality reduction. It shows correlated latent variables can be equivalent to uncorrelated ones.
Yeah, it's an identifiability point. Sometimes adding complexity, like correlations between latent factors, doesn't actually give you a more expressive model. The correlations can just be absorbed into the loading matrix.
Interesting. Exercise 8.10, independent component analysis, ICA, separating signals. What's whitening?
Whitening is pre-processing. You transform the data so it has zero mean and an identity covariance matrix. Removes correlations, sets variance to 1 in all directions.
Why do that for ICA?
It simplifies the problem. If the original data is an ICA model, linear mix of independent sources, the whitened data is still an ICA model, but the mixing matrix becomes orthonormal, easier to find.
Exercise 8.11, score matching. An alternative to MLE for unnormalized models.
Exactly. When you can't compute that pesky normalizing constant z, score matching tries to match the gradient of the log model density to the gradient of the log data density, avoiding z altogether.
Applied here to Gaussians and exponential families. And 8.12 shows standard MLE for an unnormalized graphical model example.
Right, contrasting it. Then 8.13 discusses why MLE is hard for unnormalized models, especially with binary data, and why basic score matching doesn't directly apply there either. Highlights the challenges.
Okay, Chapter 9, Sampling and Monte Carlo. Exercise 9.1, Importance sampling, why use it?
Great for estimating expectations, especially for rare events where direct sampling is inefficient.
Like estimating the probability of something very unlikely?
Yeah. Direct Monte Carlo might never hit that rare region. Important sampling uses a different proposal distribution that oversamples the important regions.
But then you have to correct for using the wrong distribution.
Exactly. You weight the samples by the ratio of the target density to the proposal density. Choosing a good proposal is key, though, and the exercise shows a bad choice, too.
Exercise 9.3, inverse transform sampling, a direct way to sample.
If you can calculate and invert the cumulative distribution function, CDF, yes, you sample uniformly from 0 to 1, then plug that into the inverse CDF, boom, sample from your target distribution. Applied here to exponential and Laplace.
Exercise 9.6, rejection sampling, another method using a proposal.
Yep. Sample from an easy proposal distribution. Then accept or reject the sample based on comparing target and proposal densities at that point, scaled by some constant.
The exercise uses it for sampling normal using Laplace as proposal and optimizing the acceptance rate.
Right, finding the best scaling for the proposal. It also mentions the curse of dimensionality rejection sampling gets very inefficient in high dimensions. Lots of rejections.
Exercise 9.7 mentions Gibbs sampling for RBMs, that's MCMC.
Yes, Markov chain Monte Carlo. Gibbs is a specific type where you sample each variable conditional on all the others. Good for RBMs because those conditionals are easy, the sigmoids we saw earlier.
And 9.9 introduces the general Metropolis-Hastings MCMC algorithm.
The workhorse MCMC method. You propose a move from your current state using a proposal distribution. Then you accept or reject based on the ratio of target densities and proposal probabilities, allows sampling from almost anything eventually.
It mentions burn-in.
Yeah, you run the chain for a while initially and discard those samples. Gives the chain time to forget its starting point and reach the target distribution. Exercise 9.9 uses it for bivariate Gaussian.
And 9.0 covers mixing and convergence. How do you know MCMC is working?
Crucial question. You look at trace plots. Samples over time should look like random noise around the target distribution.
Yeah.
You also estimate effective sample size, ESS, to see how many nearly independent samples you got, accounting for autocorrelation.
Lastly, 10.1, 10.4 briefly touch on variational inference.
Yeah, an alternative to MCMC for approximating posteriors. Uses optimization instead of sampling. Finds the closest distribution within a simpler family, minimizing KL divergence. Can struggle with multimodality, though.
Phew. That was quite a 2 or 3 pen and paper exercises in machine learning. It covers a huge amount of ground.
It really does, from like basic linear algebra right up to advanced inference and sampling.
And the focus throughout is on those pen and paper exercises.
Absolutely. And I think that's its real strength. You know, coding is essential, obviously.
Cool.
But actually wrestling with the math yourself, that builds a different kind of understanding. Deeper, more intuitive.
Yeah, I agree. Having that hands-on theoretical grasp can make you much better at applying these things, maybe even coming up with new twists.
Definitely. So if you're looking to really cement your ML theory knowledge, pen and paper is worth checking out.
And the author put the LaTeX source on GitHub too, which is great.
It is. Consider how working through these kinds of problems might seriously boost your AI and ML work.
So maybe a final thought to leave everyone with. How might really digging into the mathematical nuts and bolts of AI be the thing that actually sparks the next big breakthroughs?
Good question to ponder.
Thanks for taking this deep dive with us.